Hello everyone. Today we're going to have a look at the role that quarks play in beta decay. And the reason for that is we're about to head into the next part of the radioactivity unit where we're going to look at alpha, beta and gamma decay. And beta decay is explained through the role of the quark. So that's what we're going to have a look at in this video. But first of all, I thought it'd be useful just to take a bit of a step back and just have a look at the kind of structure of particles and their corresponding antiparticles. So in front of you, you've got the kind of tree diagram of how the model of particles fits together. So everything in the universe then is either matter or antimatter. And for reasons that we'll look at in cosmology, the universe has definitely favoured matter over antimatter for reasons that we're not quite certain of. Matter can be broken down into either leptons or hadrons. So leptons, they're fundamental, so they cannot be broken down into anything simpler or smaller. They are affected only by the weak force, so not the strong force. And examples of leptons are electrons and neutrinos. But matter can also be hadrons. Now, hadrons are not fundamental. They can be broken down into simpler parts. Hadrons are affected by both the weak and the strong force. And hadrons can either be three quark particles, which we call baryons, or two quark particles, which we call mesons. Now, you don't need to know any examples of mesons, but I put it in there because examiners do ask you questions that involve mesons. So they have two quarks. Baryons have three quarks, and the examples that you need to be aware of are the proton and the neutron. Okay, so matter can either be broken down into leptons, they're fundamental, and the electron and the neutrino are examples of leptons, or hadrons. Hadrons can exist as either two or three quark particles, and the neutron and the proton are examples of those. However, there is a corresponding tree on the other side which relates to the antiparticles. So the corresponding particles. So matter, antimatter. So we have leptons, we have antileptons, we have hadrons, we have antihadrons. We have electrons. We could say we've got the anti-electron, but we commonly refer to that as the positron. And we've got the antineutrino. So the positron and the antineutrino are our antiparticles. They are our antileptons. They are antimatter. So just trying to kind of brainwash you into all the kind of terminology that you need to be aware of. However, antimatter can also be antihadrons. So we've got baryons and we've got antibaryons. We've got mesons. We've got antimesons. And examples of our antibaryons are our antiproton and our antineutron. So a reminder that our antiparticles have the same mass but opposite charge. So in other words, the antiproton has the same mass as a proton, but it has the opposite charge. And similarly for the positron and the electron. Okay, so it'd be worth recreating this model and really familiarizing yourself with how everything fits together. But let's just break down then the baryons for a moment, because they themselves are not fundamental. They are made up of smaller particles known as quarks. And there are three quarks and three antiquarks that you need to be aware of. So there is the up quark, the down quark, and the strange quark. Now, protons and neutrons are comprised of up and down quarks only, but there are other particles that you will encounter that include the strange quark. So the up quark, 2/3 E charge, the down quark minus 1/3 E, the strange quark minus 1/3 E, and the corresponding antiquarks, and remember we use this little hat symbol to denote that we're talking about the antiparticle rather than the particle, they have the same mass but opposite charge. So we must have minus 2/3 E plus 1/3 E plus 1/3 E. So therefore, when we're putting our baryons together, our 3 quark particles together, the proton, we know, has a charge overall of +1. So the way that we would construct that from up and down quarks then is by combining 2 up and 1 down quark. Okay, so in terms of charge, we've got plus 2/3, plus 2/3, minus 1/3. Add those together and you get a +1 charge. And the neutron is up, down, down. So we've got plus 2/3, minus 1/3, minus 1/3. That charge adds up to 0 overall. Okay. So that's a little reminder of where we've come from so far. So I want to have a look at beta decay with you for a few moments and just walk you through the mechanism for how that happens and why it happens and the role that the quarks play in that. Now, it turns out there are actually 2 different types of beta decay. There is beta minus and beta plus decay. And you have encountered beta minus decay at GCSE, although it was simply referred to as beta decay. Okay, now I'm going to go beyond what the OCR course wants me to teach you, because I think it's helpful just to have a little bit of wider background knowledge on this, but also I need to just nod to some things that we're going to look at in a future unit relating to the E equals mc squared equation. Okay, so let's have a look at an example of beta minus decay. So strontium decays this way. Let's get this right. Okay. So beta minus refers to the electron that's produced, and the product is yttrium. Okay. Now we have to obey various conservation laws. The only conservation law that you need to apply for this course is charge, but actually I want to just go through it a little bit wider with you to build the story behind how we figured out what beta minus decay was all about. Okay, so let's have a look at some conservation laws then. And the first conservation law is what is referred to as baryon number. And if you do some background reading on this, you will encounter baryon number. Now, baryons are, of course, protons and neutrons. So really, baryon number in this context is a bit like nucleon number. How many nucleons have we got? So in strontium, we've got 90. Because that's the top number. You will have referred to that as the mass number at GCSE. Yttrium, also 90, and the electron isn't a baryon. So the electron's a lepton. So it's got a baryon number of 0. Okay, let's look at conservation of charge. So charge comes from the protons in the nucleus. So strontium has 38 of them, and yttrium has 39 of them, and the electron has a charge of -1. Okay, so far, so good. It looks like we're conserving baryon number. We've got 90 on the left, we've got 90 plus 0, so 90 on the right. Charge, we've got 38 on the left, and on the right we've got 39 minus 1. So all looking good so far. What about lepton number? Well, when we're talking about the nucleus of an atom, there are no leptons. Leptons, if you remember, are electrons. There are no electrons in the nucleus. So strontium has a lepton number of 0, as does yttrium. Okay, but the electron is a lepton. So it has a lepton number of +1. Okay, and for the first time then we can see that one of our conservation laws is no longer being obeyed. So we've got 0 lepton number on the left, but actually we've got +1 on the right. And so to obey that conservation law, we need something with a lepton number of -1. In other words, what we need is an anti-lepton. Okay, and that's kind of nodding towards the fact that actually there's another particle being produced in beta minus decay. Okay, and it happens to be the anti-electron neutrino. Okay, in other words, it's a form of neutrino also being emitted. Okay, let's go back to our charge and baryon conservation laws then. So the neutrino is a lepton, so it's got a baryon number of 0. So let's just check. Yes, our baryon numbers are being conserved, and neutrinos have no charge. So again, our charge conservation law is being obeyed. So all of our conservation laws at this point are now being obeyed, are being conserved. Okay, let's nod to something that we're about to have a look at in a few lessons' time. Einstein's famous equation says that kind of energy is stored in mass, and mass can release energy. Some people describe mass as just like a form of energy, and energy is just a form of mass. Now, when we have a look at the mass of strontium and the mass of yttrium, we find that there's some kind of missing mass. And therefore, there is a difference in energy between the strontium and the yttrium. Okay, so we find that the mass of yttrium is less than the mass of strontium. Okay, and so that means that the energy that corresponds to this mass is also less than that for strontium. Okay, now we have to obey the conservation of energy. Energy cannot be created or destroyed. So if we've got less energy on the right-hand side, we need to be able to account for it. So scientists did the calculation, and they discovered that there was around about 1 kilo electron volt of kind of missing energy. So they reasoned that the electron that's produced in beta decay must carry off and must have that 1 kilo electron volt of energy. But it doesn't. The electron actually ends up with a range of energies, and the maximum energy that it can have is about half that, about 0.5 kilo electron volts. So again, it's nodding to the fact that we've got something missing. We need another particle. We don't need it to have any mass, but we do need it to have energy, because we've got some missing energy that we haven't accounted for. And all of that was kind of predicting the existence of another particle, the neutrino. And if you recall, when we looked at neutrinos, we kind of said, actually, we don't know a lot about them. And they've been incredibly difficult to discover because they don't have charge, they don't really interact with matter. But you can begin to see some of the backstory which kind of nods towards the need for this particle. Okay, so a lot of that, to be fair, isn't going to be examinable, but I think it's really useful to give you that kind of background context, and particularly with the E equals mc squared equation, you will be doing quite a lot of calculations based upon it in due course. Okay. So one question that often arises is kind of like, where does this electron come from? So let's have a little look at that then for a moment. So let me just write out the equation for this beta decay that we're having a look at. Oh, let's just get the right pen. Oh, I've got no idea what I'm doing now. Here we go. Let's try again. Just ignore that rogue 90, which has appeared on your screen. So we've got the strontium
decaying into yttrium, beta minus decay, and we've got that anti-electron neutrino. Okay, what is actually going on here? At GCSE, we kind of told you that we've got a neutron turning into a proton. Now, how do we know that that's true? Because if we look at the atomic number, the charge number, for strontium it's 38 and for yttrium it's 39, so we're gaining 1 plus charge, but the nucleon number isn't changing. Okay, so the neutron is turning into the proton. And this is just one of the neutrons within strontium. Okay, and we'll get into which one and all of that another time. Okay, also producing the beta minus particle, i.e. the electron, and also the anti-electron neutrino. Okay, the energy that's released in this mechanism is what produces the electron. And again, this is something that we will have a look at. We'll have a look at particle creation. So energy can be converted into mass is something that we're about to have a look at. So the electron does not exist in the nucleus. And certainly if you combine a proton and an electron together, you don't form a neutron. The energy that's released in this mechanism is what creates that electron, which is what is then created. Okay, so as I said to you, all you need to be able to do is to balance charge. So let's apply conservation of charge again. The neutron has 0 charge, the proton has +1 charge, the beta minus particle, the electron, has -1 charge, and the neutrino or antineutrino has no charge. Okay, so we have got conservation of charge. Okay, charge on the left and charge on the right is equal. But we can now drill down another level and consider this from a quark perspective, can't we? Okay, so the neutron is an up-down-down baryon. Okay, and the proton is an up baryon, and we've got the beta minus particle and the anti-electron neutrino. Okay, we can sometimes simplify that even further because what's changed, I guess, and what's changed is a down quark has changed to an up quark. Okay, and why has that happened? That's the weak force. The weak force is changing the flavour of one of the quarks from a down quark to an up quark. And so we can summarise the mechanism for beta minus decay in this form. Okay, a down quark is changing flavour to become an up quark, and we get the beta minus particle, the electron, and we get the anti-neutrino. Okay. Now, something that I kind of think about here in terms of like how do I remember this? Okay. The electron is a particle, and the anti-neutrino is an antiparticle. So if we kind of just imagine a particle cancelling out with an antiparticle, then what I'm left with is the down quark, a particle, and the up quark, also a particle. So I've got one particle on the left, one particle on the right, if I imagine that the particle and the antiparticle kind of cancel out. Strictly, that's not what is happening here, but it's just a way of remembering that the products of beta decay. Okay, let's just look at charge, because charge should be conserved even at quark level. It has to be. So the down quark has a charge of -1/3 e. The up quark has a charge of +2/3 e. We've got a charge of +1, and we've got a charge of 0. No, we haven't. Let's just correct that. The electron obviously has a charge of -1. That's better. Okay, so if you add up 2/3 and -1, you get minus 1/3 charge. Okay, so at whatever level we consider this, charge is always conserved. Okay, and what you've got in front of you are different representations of exactly the same mechanism. Okay, and you need to be really familiar with kind of moving yourself from one to the next, but also recognizing beta decay in all of those four forms. Okay, I alluded to the fact that there are two types of beta decay. There is also beta plus decay. I'm going to do this one more quickly because I'm not going to go through all of the lepton and baryon conservation rules. You don't need to know them. That was just helpful in kind of justifying the beta minus decay. I think on that basis you'll be much happier with the beta plus decay. Now, if beta minus is an electron, beta plus is the anti-electron, i.e. it's the positron. So an example of this would be nitrogen decaying into carbon 14. And there is the positron. And this time we are going to get not an antineutrino, but a neutrino. Okay, this doesn't happen spontaneously. This requires an input of energy. But again, we'll look at that idea later. So let's look at conservation of charge for a moment. So we've got 7 protons in nitrogen. We've got 6 protons in the carbon, plus 1 charge for the positron, 0. So we've got 7 lots of positive charge on the left, 6 plus 1, 7 lots of positive charge on the right. Excellent. That obeys the conservation of charge. Now, what is happening at a kind of hadron or baryon level? A proton is turning into a neutron. How do I know that? Because there is a reduction of charge by 1. So there is a reduction of number of protons by 1, but the nucleon number is not changing, it's still 14, so therefore the proton must be turning into a neutron plus the positron plus the electron neutrino. Okay, and again, let's apply conservation of charge. Plus 1, 0, plus 1, 0. Okay, you can see for yourselves that charge is being conserved. Let's consider this from a quark perspective. So a proton is up, up, down, and that is being converted or changed into an up, down, down, plus the positron plus the electron neutrino. And I've just realized on the previous line, let's just remove that little hat. It's a electron neutrino. And in terms of just simplifying that to one final step, effectively then an up quark is being transformed into a down quark by the weak force, changing the flavor of that quark. And one final time. Okay, the up quark has got a 2/3 charge. The down quark has got a minus 1/3 charge. That's got a plus 1 charge, 0. We've got conservation of charge. So I've done exactly the same process. Okay, I've represented that mechanism 4 different ways. And again, you need to be familiar with all those mechanisms. And it's conserving charge is what you need to be able to do, okay, for these kind of mechanisms. Okay, right, one final thing before we stop. If I just show you this slide, putting together now all 4 forces that we've looked at so far, gravitational, weak, electromagnetic, and strong. If I kind of draw your attention to the relative strength row, okay, the clue's in the name. The strong force is the strongest force, and gravity is the weakest force. Okay, you guys need to be aware of the range of those forces. So gravity and the electromagnetic force act over infinite distances. Okay, whereas the strong and the weak force do not. So the strong force acts over the dimensions of a kind of a hadron, so a proton or a neutron, and the weak force acts over the dimensions of a quark. So hence the weak force is responsible for changing the flavour of the quarks, and the strong force is really holding that nucleus together. And it's worth you going back over the properties of that strong force, because if you recall, it can be attractive and it can be repulsive. But we've got this trade-off, this play-off in the nucleus, haven't we, between the strong and the electromagnetic force. So protons are repelling each other, but protons are also attracting each other. So they're repelling each other by the electromagnetic force, but they're attracted also by the strong force. But because the strong and the electromagnetic forces act over different ranges, that has implications for what combinations of protons and neutrons are possible in the nucleus. And again, that's something that we're going to have a look at in more detail in the nuclear radioactivity force. Okay, the mediating particles is not really something that is examinable, but if I just throw this out to you as just an idea that's often used to explain force, forces can obviously be attractive or repulsive. So we kind of imagine that there's this mediating particle which is responsible for the force between particles. And if you look at the two examples, there's kind of two ways that we can throw an object. We can either kind of throw the bowling ball from one person to another, and obviously there's that reaction force with both people, isn't there? So as the person on the left throws the ball to the person on the right, the reaction force causes that person to move left. And as the person on the right catches the ball, they move to the right. And that's almost like a picture of repulsion. For attraction, let's imagine that we're throwing a boomerang. Okay, and again, if you think about how those reaction forces play out, the person on the left has their back to the person on the right. So when they throw the boomerang, they're actually moving to the right. And as the person on the right catches the boomerang, they move to the left. It's kind of a picture for attraction. And so what we imagine then is that there's this mediating particle which is responsible for the forces of attraction and repulsion, and it kind of moves between particles. Okay. That's all for today. So we've had a reminder then of the breakdown of matter and antimatter, breaking that down into leptons and hadrons, breaking that down into baryons and mesons, breaking that down into quarks. We've had a look at two of the nuclear decay mechanisms, beta minus decay and beta plus decay, and we've just thrown out some ideas around these kind of mediating particles and how that gives us a picture for attraction and repulsion.